So the plan is to start some structure theory, the algebras, and so one of the main notions when you talk about structures of Lie algebra is notion of ideal. But maybe we mentioned that a few times, but now I think gave a definition. So let's start with definition. Okay, so we have a Lie algebra. And Lie subalgebra of G is called, so let's denote it somehow, I is called an ideal if the following happens, if I consider bracket of an element in ideal and any element in G, then it will be an ideal. So here y lives in I and x lives in G. So for any. So this is the definition. What's the point of this definition? It's just the same point as, like, okay, many points, but I guess the main one is to consider quotients. So in order to quotient to be Lie algebra as well, so we would like to quotient by an ideal, right? So if I in G is an ideal, then and we will write something like this: I and then the symbol. And G means that it is an ideal. Okay, then G quotient by I is naturally Lie algebra. With a Lie bracket well, I take class with representative x, class with representative y, and its bracket inside here is just a class with representative the bracket of xy, right? And if I have homomorphism of Lie algebras, so this is homomorphism of Lie algebras, then of course kernel of phi is an ideal in G1, right? And so if image of phi is G1, G2, then we have what's called homomorphism theorem, which says that G2 is G1 quotient by kernel of phi. So some elementary stuff, but we still have to spell it out. Okay, so the next notion is commutant of two ideals. So if I have two ideals, Then the commutant of I1 and I2 by definition, so its notation is like that, and this is by definition linear span of such things of all brackets x1 and x2, where x1 belongs to I1 and x2 belongs to I2. So not only, so don't, I would like to stress only here is that it is not on like not just the pure brackets, but linear combinations of them. Okay. Okay. So let me define now what is called the derived series. The derived series. Of a Lie algebra G is a sequence of ideals of G. So I have G itself, then I have ideal which is denoted as D1 G, and then D2 G, which is ideal of G, but also ideal in D1, and so on. Right, where so this one also can be denoted as just D0, right, of G, and this one is just as D of G. This is just notation, just another notation, right? And we just need to.
So it's infinite.
It depends, right?
No, but in your notation.
So it's infinite, but it can be it can stabilize at something. Right. So where so I have to define. So the recursive definition. So di plus 1g is just a commutant of di g and di g. All right. So let's. So everything will be pretty easy today until we get to the Lie's theorem, which is also linear algebra, but kind of, you know, you have to work a little bit to prove it. Yeah, so Lie is about solvable. So today we'll cover solvable. Maybe next time nilpotent, which is like an English about nilpotent. So let's prove the following lemma that we will use from time to time. First of all, G over dg is abelian. And on the other hand, if I have an ideal, if I quotient by this ideal, so if this is abelian, then I actually contains, so dg is inside I. So this is sometimes called derived Lie algebra, d1g, dg, d1g. Okay, which is minimal algebra, minimal ideal inside G, such that if we quotient by 2, get abelian. Right? That's what this lemma says. Proof. Well, first one is almost like just obvious, right? So you take the commutator of this class with this class, it's X just by definition this, right? But this one belongs to TG, right? So this is just because this one inside G. So then when you quotient, this just becomes 0, so therefore it's abelian. Second, to prove second, let me denote somehow canonical projection from G to G bar is it's just a notation for G over I. Okay, and we have that pi. So we have pi of dg. So this is a homomorphism, right? And so this therefore we have this d. It's just dg bar. Well, at least it's like that, right? But it's actually
The quality is only for subjective.
for surjective, right? Well, it is surjective, yeah. But for any homomorphism, this is true. And then, but this one is 0 by part 1. So therefore, dg is inside I. Easy as that. Okay, and finally, let us introduce solvable Lie algebras. So G is called solvable if there exists some number k, right, some natural number, or maybe even 0, I don't know, such that dkg is just 0 ideal. So in other words, the derived series, if it stabilizes at 0, then the algebra is called solvable. Okay, so we have the following proposition. Yes, so it's a criterion of solvability. So proposition. So just I think I will need G to be finite dimensional in this case. So let G be finite dimensional. Then G is solvable is equivalent to the following. There exists a finite sequence of ideals of G. Well, ideals, I will denote them as AIs. A0 will be G, then A1 is an ideal inside G, A2 is an ideal inside. Well, I even can say they will be ideals, but I know I would like criterion to be weaker, as weak as possible, so I can say subalgebras, right? But they are ideals, so it's a sequence, and one is inside another, and this next one is an ideal in the previous one. And have the last one, so it's finite sequence, which is just 0. And I would like, in this sequence, the following property, that AI, quotient by AI plus 1, is abelian. Well, for every I from 1 to k, well, to k minus 1, right? From 0, I guess, right? I would write g by 1 to be also abelian. Okay, proof. So first, let's see. So this is an easy direction. I just take AI to be d. Okay, so we have upper index dig. It's clear, right, that they satisfy. Just because of lemma, right? Di plus 1 is the derived algebra of di. So therefore, when I quotient, it's abelian. This direction. So let's prove that di G is inside AI by induction on I. Right. So what I need? I need to write di. So first of all, d0 is, of g is g, and a0 is, so base is obvious. And then I have di plus 1g. So this is by definition, it's just dig, dig. And this is by induction assumption is inside AI, right? And this is d, so this is dAI, right? It's derived algebra. But dAI is inside AI plus 1. Right? This is just because AI plus, so AI quotient by AI plus 1 is abelian. So therefore we have this. So this is an ideal quotient by AI. We get an abelian, so therefore derived of AI is inside this ideal. Again by Lemma. All right. Let me see. So I'm starting to ask myself what breaks if I have not finite dimensional. So let's think together. So again, this definition of solvability, I guess, works if it's infinite dimensional as well, right? So I just have some sequence of. So it just stabilizes at 0, right? Still. So if I erase the first line, right, I will, I still would like to have finite sequence of subalgebras, so such that it's abelian. So I take AI. So I think this direction still works. The other direction, and and that direction is okay. So since seems like I can erase the finite dimensionability, but okay, just to be sure, I will leave it there. But I think this is redundant. So what's so my next goal is to give you like a standard example of solvable Lie algebra. So let me fix some vector space. Let V be well, let's say it's complex. Be a complex vector space. And let me consider a flag. What is a flag? It's a sequence of vector subspaces of V. Right, so flag is the following data. So you have sequence of subspaces, and Vk is V. And this is, let's call this 0 to be, I don't know, V0. And I define the Lie subalgebra inside GLV that depends on this flag as follows. It's just X and GLV such that XVI is inside Vi for all I from 1 to K, right? So proposition is that if I take my flag to be complete flag or full flag, I don't know how. Let's fix the term full. So if F is a full flag, which means dimension of Vi is I. In particular, dimension of V is K, right? So each time my dimension drops by 1 from Vi to Vi minus 1. Then B of F, so this is solvable. Okay. So these are just upper triangular matrices.
Yes.
In some bases, and this basis I fixed by saying that I fixed a flag, right? So if my flag is not full, it's block upper triangle.
So the space of flag is simply the vector group of GL over upper triangular matrices.
GL over yeah. So it's as we learned, it's a homogeneous space.
Yes.
So yeah. All right. So let's prove it. So we define AJ of F to be the following. It's X in G of V, right? Such that X Vi is inside Vi minus J. So A0 is, of course, then B of F, right? so for all I from 0 to k. All right. So then, well, AK is just 0. A0 is just B of F. What else? You have also AJ is inside AL if J is greater or equal than L. And if I compute the commutant of AJ and AJ, it will be inside A2J, right? Because, well, it's just a composition of elements from here and here in two different ways. So I first decreased index by j and then decreased index by j another time. Yes. So it's inside A2J. For every j from 0 to k, well, in particular, AJ is the Lie subalgebra. This shows of B of F. Well, if my j is greater or equal than 1, then of course 2j, right, is greater or equal than j plus 1, and AJ and the derived algebra is inside AJ plus 1, right? It's inside 2j. 2j is greater, so it's inside this. And therefore, AJ by AJ plus 1 is abelian. And this is almost everything that we need, except when j equals to 0. Right? When j equals to 0, then this equality is not true. So we have to, so it is left to prove that if I take A0, so which is B of F, compute its commutant, then it's inside B itself, of course, but we would like something stronger. It's inside A1 of F. Yes, and by the way, this thing is called N of F, and this will be a natural example of nilpotent algebra, which is strictly upper triangular matrices, right? But is it clear why this is enough to finish the proof? So what is left is that A0 by A1 is abelian, right? Then we'll use the proposition that we proved before. So A0 is B of F, right? So if derived algebra of A0 is inside A1, then therefore A0 by A1 is abelian. So therefore, if I prove this, then I proved the missing link in my proof. Okay. Okay, so let's prove this. It's also not. It's also not very hard. So let me fix two elements in B of F, and then, well, I will also fix a basis. Vk of V, well, such that, well, Vi is inside Vi set minus vi minus 1. So then I take x, act on vi, right? And I get some number times vi plus something which is inside vi minus 1. Right? So that's where we need actually the flag to be full. Right? We actually need this every time additional vector, just 1. Right? So if I take y vi, so it will be some other number bi, but the same vector vi, plus something inside vi minus 1. And so therefore, if I compute the commutator and apply it to vi, right, it will be ai bi v minus bi ai v. So, but this is just numbers, ai and bi. Right, so this actually cancels, and what is left is something inside vi minus 1. So therefore, if I apply something from the commutant, it shifts my index by 1, so therefore x, y belongs to a1. And so we finished.
So we've shown that there exists a sequence of ij, yes?
Mm-hmm.
Yes.
And ak is 0.
Yes, okay.
So, yes. Okay. Another useful proposition which says that if I have I and G over I, so this is an ideal in G, are solvable, therefore, therefore G is solvable. Sure, yeah. No, not n though. So wait, yeah. So if my G is solvable and I have an ideal inside, then it is also solvable, right? Yeah, sure. If and only if. Yeah. But this direction is really obvious, so let's prove this direction, which is again not hard. So proof. Again, let's denote this time. For some reason, I denoted the projection by p, not pi. So G is a projection, and then so let me take an element of derived series, project. So it will be, because of surjectivity, right, dnp of G. But I can find an n such that this thing is 0, because G over I is solvable. So for some m.
It just follows from the fact that P is a
Homomorphism of Lie. Yes. Surjective. If it's not just homomorphism, it's just inclusion, but inclusion is still okay here. All right. But then it means that dng is inside I. All right? Because we quotient by I, and so dn, since it becomes 0, it's inside I. So therefore, dn plus k. So then we take and then we derive sufficient number of times more, right? So it's inside dki, and dki for sufficiently large k is just 0 for some k, right? It's just from the solvability of I, and we're done. So there's number such that an element of derived series corresponding to this number is just 0. All right, so now it's a hard theorem, which is sometimes called Li theorem, but because it's the hardest part is in this statement. So theorem let rho it's a representation of a solvable Lie algebra. So let rho, it's a homomorphism from G to G of V, B complex finite dimensional representation of a solvable Lie algebra. By the way, so Lie algebra G. By the way, I don't care if Lie algebra is real or complex, but I care that representation is complex. Then there exists a vector in V, which is common eigenvector for all rho of x where x is from G. So for solvable Lie algebra, if I have its finite dimensional complex representation, I can find a common eigenvector in this representation. Okay. Proof. So we'll prove it by induction on dimension of G. Yeah, and obviously I would like here to take G to be finite dimensional. Otherwise, my proof will not work. So by induction on G, on dimension of G. Yeah, so how to, I mean, if so let's discuss. So it's kind of tricky how to make a step in this induction. So we'll need some solvable subalgebra inside, which is of dimension less. So we have this, right, the derived algebra of G. And we know for sure that it does not coincide with G. Right? Otherwise we stabilize at the first step of derived series and never get to 0, of course. So therefore I can find at least vector space, vector subspace such that codimension of G prime is 1. Right, there's something in between. Okay, and I didn't finish. I would like the commutant to live inside G prime. So there's something in between commutant and G. And I would like this maximal something to be G prime. Right? Okay. I claim that then G prime is an ideal in G. Because, okay, let's check. So indeed, if I take, say, A in G and B in G prime, compute A, B, right? But it's inside G, right? So it's inside G prime. So it's an ideal. Moreover, it's solvable. Well, G is solvable, it's an ideal and solvable. Yeah, so also G prime is solvable. Right? So we figured that an ideal of solvable Lie algebra is solvable. And it's an ideal and solvable Lie algebra. At least for this reason. But you can also, prove by induction that di, well, it's just, I mean, you can prove by induction that di of G prime is inside di of G, which is just proving that ideal of solvable is solvable. So our induction in dimension G works, right? So G prime is solvable of dimension less. So therefore, by induction assumption, induction in this induction, right? Well, anyways, we had only one induction here. There exists vector V such that it's a common eigenvector for all elements of G prime. So rho of H, V, is lambda of H, V. So for every H in G prime. So this is just, for every H we have number, lambda of H. So this is just a complex number. So we just label it like this, lambda of H. Actually, it's linear functional, but whatever. Let me take G prime. So since it's codimension 1, right? I can write down G as G prime plus Cx for some x and G. And let me define now vectors v1, v2, and so on. So maybe starting with v0, right? So Vi as I runs from 0 to infinity, as follows. So V0 is just V, and then Vi is X applied to Vi minus 1. Also, let me denote, let me take the span of these Vi's, and let me denote the span by W. So our goal is to prove that every vector in W is an eigenvector of G prime. So then we will be almost done, because then you can take so then you can take this V, right? So it's a invariant subspace with respect to this Cx, right? So it has an eigenvector. W has an eigenvector for x. At least one it does have, right? So all of them are eigenvectors for G prime, and at least one an eigenvector for x. Therefore, we will be done, because it will be eigenvector for the whole G. Okay. So the goal to show that any eigenvector, any vector in W is a common eigenvector of G prime. Okay, we'll do it in 3 steps. So step 1, I claim, so claim 1, that for any h from G prime, the following holds. If I take h and I guess k from z greater or equal than 0, h vk is lambda of h vk plus some linear combination over VLs with L strictly less than k. Linear combination with some coefficients a, k, l, which depends on h as well. Proof of the claim by induction on k. Well, step is clear, right? V0 is just V, and that's how we defined actually this number, lambda of h. This is the base. So base obvious, and step, I just need to act and commute, right? So I will take h vk, and I need to write what is vk. It's x times vk minus 1. So it is x h vk minus 1 plus the bracket, the commutator, right? Vk minus 1. So this guy is some h prime, but it also belongs to G prime. This one, for this one, by induction assumption, we have this formula, right? So therefore, it is x, and then we plug in this form of OK minus 1. So we will have lambda of h v k minus 1 plus sum L less than k minus 1, a k minus 1 L of h VL. So this is this guy plus, and again we apply this formula for h equals h prime and k and for k minus 1. Right, so we'll get lambda of h prime vk minus 1, right, plus, I don't know, some sum a k minus 1 L, L less than k minus 1 of h prime VL. Anyways, if you look what so the only vk that we'll get is from this. So x goes through, hits vk minus 1, we have vk. So it's lambda h times vk. And everything else is just this sum. So it's sum over a k l depends on h v l as l less than k. Okay, so this for some numbers a k l of h, and here also some numbers a k l of h. So we proved claim 1. We need the following observation. So actually, so we have this vi's, right? So let me remind you, vi is x vi minus 1. So I have v0. So I start, going one by one through this v, and at some point I will have linearly dependent set, right? So so all the vectors before will give me basis of w, right? So v0, v1, v dimension of w minus 1, right? Because I started with v0. It's a basis of w. It's just simple exercise to see that after that they will can be, so all other v's can be linear combinations of those. Once we hit like the maximal linear independent subset. Okay, so and in this basis, by claim 1, we have some upper triangularity here, right? So rho of h. Well, first of all, g then w, right? By claim 1 again, w is sub-representation of g prime, right? So I never go outside of w. On the other hand, if I take rho of h and restrict to w, I'll get some upper triangular matrix in this basis with diagonal entries are just lambda of h's. Something here, 0 here. This is for any h from g prime. So therefore I can compute trace of rho of h over the space w. And this will be dimension of w times lambda of h, right? So I just sum up the diagonal entries. Okay. But also, so in particular, if I take trace of W of rho of the following element of H, the bracket of H with X, and this X is the one that we fixed that G is G prime plus X. So on one hand it's just 0, right, because it's a homomorphism, so trace of commutator is 0. On the other hand, I can apply this formula and say see that it's dimension of W times lambda of H and X. So therefore, lambda of this is 0. So this will help us in step 2. So claim 2 for any H and G prime and K from Z greater or equal to 0, we have that H, the commutator acting on Vk is just 0. Proof, again, induction on K. Well, we know that H x acting on V is a base V0, right? K equals 0. It's just lambda of Hx acting on V, right? Lambda of Hx is 0. So therefore it's 0. Okay, step. We have Hx applied to Vk is, well, again, we need to remember what is Vk. It's x Vk minus 1. Again, so I need to commute this x with Hx. So I get x Hx that hits k minus 1. So this is gone, right, because this is 0 by induction assumption. On the other hand, so plus the commutator, right, of H and X with X. And it hits Vk minus 1. But this guy is inside G prime. So it's just some other H prime with X. And it hits Vk minus 1. And again, by induction assumption, this is 0. So 0 overall. Okay. And finally, so we proved upper triangularity, in a sense. So now we would like to prove that it's actually diagonal. Right? So claim 3 is that HVK equals to lambda of HVK for every H and G prime and K from Z greater or equal than 0. Which is just finishes for us the step of induction, right? So again, proof of claim 3 is by induction of K. So V0 is obvious, right? So k equals 0, just obvious. That's how we defined V. And then h vk is hx vk minus 1. So I commute h hits vk minus 1. By induction assumption, this will be lambda of h vk minus 1. And then x hits it, right? So therefore it will be lambda. Okay, let me not skip it. So h lambda of h vk minus 1. And then commutator. So this is 0 by claim 2. And then x goes through, hits vk minus 1, we get vk. So it's just lambda of h vk. So we're done. Okay, now we already discussed it, but this finishes. So therefore, what did we get? We get that w is every vector in W is an eigenvector for G prime. Now, an eigenvector of W so let me put it this way. Now a vector of W, which is an eigenvector of X, will be an eigenvector of the whole G, of course, because G is G prime plus Cx. So this proves a step of induction for us. Okay, what about base? Base should be, so step of induction is proved. What about base? So the base is dimension 1, right? Dimension 1, so I have a representation. So I have a representation of just R, right? Which is just one matrix. Right? One matrix should have an eigenvalue. So base dimension G is 1. Right? So it's just R or whatever C goes to I guess T goes to T A, where A is some endomorphism of V. And so eigenvector, so take eigenvector of A. So take eigenvector of A. Okay, so that's, we proved the statement. So we'll have a couple of corollaries that follow almost immediately from this, and then finish.
Easier to prove the solvable Lie algebra. You can find the basis in the representation with respect to which it's up the triangle.
So that's
I like that.
almost it, right?
Yeah, but that claim is
no, I'm not sure that this claim is easier to prove. I think kind of the same.
No, it's like 1 page.
There, knowing you is 1 page if you claim something that is proved using 3 pages, okay? So I don't believe you. Yes, so you might be right, but I would be happy if you show me after that, okay? But first corollary is that actually any irreducible complex representation of a solvable Lie algebra is one-dimensional. Proof just the subspace spanned by the vector from previous theorem is an invariant subspace. So therefore, any representation has a one-dimensional invariant subspace. So therefore, any irreducible is one-dimensional. All right. So, and corollary 2, I don't know. Let's say theorem. And this is usually it's called Lie theorem. That so let again rho from G to G of V be a finite dimensional complex representation of solvable Lie algebra G. Then there exists a basis of V such that all rho of x as x runs through G are in upper triangular in this basis. Let's prove it. Proof is by induction in dimension of V. So for dimension V equals 1, nothing to prove. Every matrix is upper triangular, right? Every 1 by 1 matrix is upper triangle. If dimension V is greater than 1, take V from the previous theorem, right? And then consider V quotient by CV. It's another representation, so it's an invariant subspace. This is another representation. So this is another representation. And by induction assumption, there exists, so it's dimension one less, right? So there exists some basis of W such that rho W of X is upper triangular for any X in G. But then you take so take any lift of these W's to V, right? So take any lift, and then let's denote it W1, Wn, tilde. So this is of Wi's to V. And then I can consider the following basis. V, then V, then W1 tilde, Wn tilde is the basis of V that we need. That's it. Okay, so let me stop right here.